Hello and welcome. I'm Andreas. I work as a trainer and consultant primarily for C++. And I'm also the creator of C++ Insights. And this is also the tool I like to talk about in this series. So while we already talked about template instantiations and how that works, and in the former episode about the difference between marking a function in a class template virtual or not, I like to talk about variadic templates today. So the example you're looking at here essentially is a function min, which takes an arbitrary number of arguments and figures out which one has the minimum value in it between or among all them. So let's start from the top to the bottom. At first, in line number 4 and 3, we start seeing the template head with a type name t, and then in line number 4 we see a type name ... ts. And as the comment points out here, this marks a variadic template. We see the type name with the so-called ellipsis after it, and this is a parameter pack where ts can contain 0 to multiple types. We can also do this with non-type template parameters, but in today's episode I like to solely focus on type template parameters. Now in line number 6 we see that the method is constexpr and it returns auto, and then in line number 7 we see that the name is min and that it takes 2 arguments, const tref a and b, and as a third argument it takes a const ts reference, and then we once again see the ellipsis, the ... ts, and that one is now the parameter pack. So when you can say at the top in line number 4, it's more a type pack, it's a pack of different types. In line number 9, we are dealing with parameters. As you can probably guess from what you're seeing here, you can declare this arguments as with any other template argument, with const, without const, with reference, with r-value reference, with a pointer, or whatever. Okay, your type of course has to provide this and your arguments have to match here. But in my case, I say, okay, I like to take things by const reference. And then inside in line number 11, I place a first call where I say that I create a new variable m, and that one contains the minimum of a and b. So the 2 parameters that are always there. And now because my standard is C++ 17, because their variadic templates are so much cooler, because I have a constexpr if there. I don't need to do recursion all over the place and then write a terminating function. Here I can do the expansion using a constexpr if. And in line number 12, now I use this constexpr if, which is a compile time if, and it checks whether the size of ... ts is greater than 0. And the size of ... is another special thing that comes with variadic templates. It tells the compiler to query the number of elements in this parameter pack. So the important difference here is we are not talking about bytes, we are talking about number of elements. Say I'm passing 3 parameters into this parameter pack, then the size of will return 3. But as you can see, I cannot have also the option to pass no parameter to that pack. This would be line number 20 below, while line number 19 passes the 3 parameters or 3 values to this pack. So I can also decide to pass nothing to this pack, and then it's simply empty and the size of returns 0. So the constexpr if here with the size of ts now checks whether there are elements in the pack left. And if that's the case, then min gets called recursively, and now I'm passing in m, which was previously calculated in line number 11, and the parameter pack, or here now there are values. And in line number 13 here, you can see once again the ts ... So at this point, the pack gets expanded. We are unpacking this parameter pack and passing it to min. And the key here is that by providing only m and then the pack, I essentially split split up one element of the parameter pack each time I'm doing this recursion. And by that, I'm decreasing the number of elements in that pack until I reached 0 elements in the pack, and then I only have the two parameters a and b, and that's when the size of yields false or 0. So I'm not going into this constexpr, but in line number 16, and I'm returning the final result of whatever error is less than it was before. And we can now see that this function min is able in the static assert below here to calculate a minimum of 3, 2, 3, 4, 5, or simply of 3 and 2. So this is a very handy way of getting the minimum of multiple values. And if I now transform this, then we can first of all see that it's working, because otherwise the static assert would trigger and we wouldn't get the transformation here. And now we can see what's happening. So the compiler creates me a instantiation for min with 4 ints. So 2 are already there. These are for my arguments a and b. The other ones I'm seeing here. That's ts2, ts3, and ts4. So why it's 3? We need one for the first t, and the other 3 are from the parameter pack. That's why we are seeing 4 arguments here, and the number doesn't match necessarily the number of parameters here. So the first one covers a and b, and the next 3, they cover ts2, 3, and 4. The names are made up here. Compiler doesn't need to give that things names. It thinks in other terms. Now we can also see that here my constexpr if, it returns true at compile time. So this branch here is active, and min gets called recursively. Now we can see that it gets called with m, and then ts2s, ts3, and ts4. So that's quite interesting, because it's the very same we could write ourselves. If we dig down a little more, then we see here, this is the next step of the recursion. Now min gets instantiated with only 3 ints. And once again, the first one donates to a and b, while the other 2 are for ts2 and ts3. And inside the body, we now see that min gets called with m, ts2, and ts3. And then in the next recursion step, we see min instantiated with only 2 types, 2 times int. Once again, first one is for a and b, and the second one is for ts2. So now we have only one parameter in the parameter pack. So our size of still returns true. And here we see more or less the final call to min with m and ts2. And here in line 36, we see the final instantiation. We see that min gets instantiated with a single integer. It's for a and b. And my constexpr if now is empty because it evaluated to false. So the contents in there are gone at compile time. So min is no longer called recursively, but instead the result is returned directly. And now we can see here below that 2 static asserts passed. So this is how variadic templates work. And if you look at them, then as I said, it's the same as we could write by hand. So it's just handy because we don't have to write all this code ourselves. Okay, in a different version of this function, it would also work with different types. Here, the version, how it's written with a and b being of the same type, prevents mixed types effectively. But in general, you can write it differently and then mix your types. I would always be cautious with that. But the brilliancy is we don't have to write this code. We have to write it only once, and the compiler generates all the different variations, all the different instantiations for us. Which is great because we have to maintain only a single function, bug fix that one, and we profit from it all over the place. Which is what I really, really like about templates in general. There is another difference I like to point out. You may know this ellipsis notation as we see it here in a slightly different way from, for example, printf. So we have variadic functions. We had them before C++11, before variadic templates came around. Printf is one poster boy example. There's a huge difference between these variadic functions and variadic function templates, for example. The regular variadic functions, as we had them all the time, they work by putting all the values on the stack. And then you have to fish them out from the stack, and you have to say which type you expect that value on the stack to be of. This is why printf uses the format specifier with %d, because the compiler doesn't care anymore which value is there on the stack of which type it is. So it's not strongly typed. But we are in C++, and in C++ we like things to be strongly typed. And this is what we get with variadic function templates, for example. Because if you look at the signature the compiler creates for us, here it knows the types, okay? It is very careful about them, like it always is for function templates or templates in general. So we do not get implicit conversions here, and we profit from all the other parts. So if I would say that I pass here a 5.0, then the compiler would say, oh no, I don't compile this for you, because at the very end I have a combination of int and double, and they both belong to parameter t, and I don't know how to instantiate such a function template. So you effectively prevent mixing types with the version how I wrote it here. In general, even if you allow this, then you still know the type. This is one thing that, for example, std_format uses. It's heavily based on variadic templates, because there you know the types. With std_format, we only have to be specific if you like that this special formatting or something like this. But by default, like IOStream as well, they know what types we put in, so they can format it accordingly by default. This is the big difference to, for example, printf. Here we have the things, we do not put something on the stack and have to randomly say, oh, give me that one and treat it as an integer. Oh, it was a std string, that's too bad. So this is, in terms of type safety, why variadic templates really excel there. I hope I could teach you one or other thing about variadic templates in general, and why they are so great to use and why it's so beneficial to use them for more robust code and then in general for type-safe coding. That's it for today. Stay tuned for the next episode. Bye bye.